No, I didn't, but I think it's okay. Hey, good, thanks. But so no, this is good though. I wouldn't have been able to do it by myself, right? We actually had the help of the whole class here. But each and every one of you can understand and believe that it's true. I mean, someone, like I said, someone much more clever than any of us, including me, came up with, why don't we use the law of cosines? Why don't we use the distance formula? Let's set them equal to each other, and it's going to show us what we want to, prove. That was really clever. It was really smart. Like, I wasn't going to do that, and none of you were going to do it. But as students of math, we can all read through it, appreciate the fact that someone far smarter did it, be convinced that it's true, and then go on saying, all right, fine. Now I can use that. I feel okay.
In like 15 years, they republish a textbook, and they actually do formulas, and all of a sudden you see like Corbin having a new formula.
Could be true. Oh, this is bad.
Debug.
Oh, that wasn't that bad. All right. Now that's all small, though, right? So we also know that cosine of a sum is cosine alpha cosine beta minus sine alpha sine beta, right? That's the second one. So far, so good. Sine alpha plus beta, what's that? Sine alpha cosine beta, and then sine keeps the sine, plus cosine alpha sine beta. And then finally, the sine of a difference. Okay, so those are the sum and difference angles that we learned yesterday. And remember, if you memorize one of them, the rest are based on a pattern. Like you can recognize the pattern. And actually, we said yesterday, if you know all four of these, you actually don't need to memorize your double angle formulas, because these give you the double angle formulas. Okay? All right, so I proved one. I'm not going to prove the other three. Are you okay with that? Please say yes. We can, if you're interested, we can do the proofs for the other three today after school. Okay. All right. All right. So, my impression is right, and I sense that you understand what I'm saying. Look, you can probably appreciate the fact that one of them can be proved and don't need all four of them to be proved. But, like I said, there's some of you who probably would have been fine if I just put this up in a box on the board. You would have been like, fine, no problem. I believe you. You're the teacher. But it is important, every once in a while. Like, ask your teachers, hey, why is that true?
Your power as a math teacher. You put up some kind of formula and we'll use that on some exam tests in college.
There you go.
Yeah. Or no, if you put x's and cosines and tangents in there and then it had it equal to 3, we'd all been like, all right. And write that on some exam tests for college. All
right, Elizabeth, what do you got? Yep. All right, so the next thing I want to do is make an observation, and it's actually different from these trig identities. So, I want to put the trig identities away for a second and do a little, exploration on our calculator. All right? Say yes. Yeah. All right. So, get out your calculator. Yeah.
My calculator automatically goes to degrees every time I turn it off and on.
Really?
Yeah.
I can't tell if that's really cool or really frustrating.
Maybe that's
the latter.
Okay. All right, so... Really? I'm so bummed about that. Do you think someone, I think it's an honest mistake. Yeah.
What's a mistake?
All right, so I would like it if you graphed sine of 2x plus the cosine of x. And you need to make sure that you are in radians. Nope. And you're in function mode. And I think I'm going to start with like maybe a zoom decimal and see how that goes. Well, check that out.
Wait, sine of 2x plus cosine.
Sine of 2x plus cosine of x. And I get this graph that actually, it is periodic. It repeats itself, but can you see that it's actually sort of like the hills and valleys aren't always equal? Is that all right? Okay. Let's go back and do sine of 2x plus the cosine of 2x. And graph that. Huh. So this is periodic, and it looks like the hills and valleys are equal. All right, let's keep exploring because this is interesting. What if I did sine of 2x plus the cosine of 3x? Let's see what happens there. Whoa. Oh, check it out. All right, so it's still periodic, but the hills and valleys aren't all the same. Let's go back and do sine of 3x plus the cosine of 3x. Huh. All right, so Travis is ready to make the observation that I think a bunch of us have been, at least I hope, thinking, if not saying. So, Travis, state your observation again.
When they're equal, it makes it somewhat equal.
All right, and when you say when they're equal, what do you mean by? Be more specific. What's equal about the sine of 3x and the cosine of 3x? The period. When the period of the functions are equal, we get not just a periodic function, but we get a function that actually looks like maybe just a single sine function. Like, I bet you we could actually figure out what this function is and just write it instead of in terms of a sum, we could probably just write it as one function, sine or cosine. Let's see, what happens if I insert a 2 in front of sine of 3x? What if I change the amplitude? Do you think that's going to mess things up? Sam, wake up. Sit up straight. There you go. Your mom would be proud. Okay. Well, the amplitude definitely changed, but is the function still sort of, as Travis said, nice and even? Yeah, it is. And so the observation I want to make is actually the observation that Travis made. That when you add two sinusoidal functions, if the periods are the same, then you can actually write it as one sinusoidal function. You don't need to write it as a sum. You could write this same equation using just one sinusoidal function instead of the sum of two. And I want you to see that observation. Do you believe the observation? All right. And in the book, there's actually a conversion. And so I want to show you the conversion and then show you that it's true. But more important, I think one of the homework questions, you have to do the conversion. But more important to me than you doing the conversion is you just understanding that if you have a sum of sinusoidal functions and the periods are the same, it can be written as one sinusoidal function. So I'll summarize. If you have a function that's let's see. Hold on, let me get this straight. Yep, all right. A1 sine of bt plus A2 cosine of bt. That is the sum of a sinusoidal function. Okay? That actually, if the periods are the same, like Travis said, I can actually rewrite that function as A sine of bt plus theta. And there's some very important things. there are some very important conversions. The first thing is that capital A is the square root of little a squared 1 plus little a squared 2. B is equal to B. Remember that one? Come on, say yes. Thanks. And then theta is equal to the inverse tangent of A2 over A1. So, you can convert the sum of sinusoidal functions to a single sinusoidal function as long as they have the same period. That's interesting. It is. No, that's pretty cool. Like, instead of writing something as a sort of complicated function, you have a way of condensing it into something that's a lot simpler. So let's take, what were we looking at? We were looking at 3 sine of 2x plus cosine of 2x. We can rewrite that as a sine of bt plus theta. All right, a, b, or theta. Take your pick. All right, what's b equal to, Evan? Yeah. It is. Oh, this should be x. I'm sorry. What's b equal to in this case? Don't say b. Say it loud and proud, Monty. 2. So it's going to be 2x. All right, now I have a and theta. Call on someone, Evan. You need your calculator. Oh, maybe not. Not for a. Maybe you can do that in your head. This?
Do it in your head.
You can do this.
Do it.
What's little a1 squared? What's little a2 squared? What's in front of cosine? 1. So 3 squared 9 plus 1 squared 1, 10 root 10. Okay? And now the last one I do not think anyone's going to be able to do in their head. I need you to do the inverse tangent of 1 over 3. And you need to be in radians. Are you in radians? If you are you? No.
I didn't actually.
Oh. Miles, I saw you do something.
Yes. In radians?
Yes, please.
Let me make sure. Yeah, okay. 0.3217.
0.3217. So, I think this is interesting. I think the fact that this whole function is equal to this function, and one is the sum, and one is an ugly non-sum, is pretty interesting. And I actually think we should go take a look at it on our calculator. Let's see. My claim is that function... Oh, my gosh.
Oh, my God.
What was it? We said 3, and we did this as 2, and this is 2. Okay. All right, so my claim is that function... And I'm going to turn this guy onto the bubble guy. I love the bubble guy. Is the same as square root of 10 times the sine of 2. Wait, we're not there yet. Hold on. Plus 0.3 what? 217. So I claim that they're actually the same function. There's just different ways of writing it. And if we go to our graph, there's the first function.
Oh, no wonder. I'm in radians.
Yeah, you need to be in radians.
No, I am in radians.
Oh, here's the second function.
Mine is now.
The second function's right on top of the first function. That's crazy. You're telling me that they are the same function? Unbelievable. Unbelievable, Max. Unbelievable.
Unbelievable.
Look. Yeah, it does look like the bubble guy's going on a roller coaster. So look. He does. Don't you wish you could be on a roller coaster right now? All right, so look. You can convert. No, I was totally in radians. Mode, I'm in radians. Wait, I'm not lying. Rafaela.
Mine was Canadian. I didn't know. Maybe you forgot an X or something. I don't know what's happening.
So look, at the very least you're quiet. You can convert the sum of sinusoidal functions into a single sinusoidal function. And this is the key. Okay? That's the key to converting. Alright, so there it is. You hung through a proof. And then you made an observation, and Travis and Raffaella made an observation about the periods of two sinusoidal functions being able to be expressed as a single sinusoidal function. And not only that, I gave you the key to unlocking that. And now we have about 5 minutes left, and I'd be happy to do like one of the trig identities from last night. All right. So if you want to take a look at one of them, I'd be happy to do it and sort of facilitate that. All right. I'm going to read.